I'm gonna. Okay, so I hit the recording. We should be fine. So
actually didn't look to put the.
I can
start
stop it.
with the front.
I can stop it if you want, and we can go at it again if you need to change something or you need to swap screens or whatever.
No. So is my screen displayed because I don't
yeah,
see.
we can see your slides now.
Okay, so
we can see your slides. Yeah,
the first page.
The first page exactly. Yeah.
Good.
So hello everyone. To do a quick introduction, this is Ulrich from Polygon 0, if I'm not mistaken. He's the author of many interesting papers. Some of them have been have appeared lately this year, quite recently, and one of them is LogUp, which is basically some kind of way to have much better or much cheaper lookup arguments using GKR, and therefore also trying to lower a bit the commitment costs for the witness. But he's definitely one that should explain all of that. So thank you very much, Ulrich, for coming here and for explaining everything to us. As Ulrich mentioned at the beginning of our chat, he's happy taking any questions during his talk. So if anyone has any kind of question, just feel free to jump in and ask. The floor is yours, Ulrich, whenever you want.
Thank you. Thanks for having me. So actually, before we start, so I'm going to talk about LogUp, but an improved version of it. It's a joint work with Shaha Papini. We put it on AISCR. When was it? Like end of August, beginning of September. So, okay, so roughly, I mean, let's first discuss the use case because there are so many lookup arguments. So the use case we are targeting is not the large table track that is followed starting from Baloo going up to lookup and CQ, not that kind of track. So we are considering the use case where we have a typically ordinary size table, but ordinary, I mean, it's as long as the trace is, say it's 2 to the 20 at maximum, maybe 2 to the 25, something like that. So no large table lookups or the classical ordinary size lookup tables. But what we face in many applications is we have a lot of witness columns. Is my mouse cursor displayed?
Yes, it is. We can follow it. Yeah.
So I can use it as you can use it as a pointer. That's fine. So we have a lot of columns, and these columns are all subject to one and the same table. So what are specific examples of that? For example, in the context of the CKVM, in particular the one from Polygon 0, we have a lot of columns that are subject to the machine word size proof. So they're subject to one and the same range proof. I think I always have to ask my people how much, but it's beyond 80 columns, 80, beyond that, which is subject to a 16-bit range check. So, but also other applications we might think of a hash-friendly circuit-friendly hash function, circuit-friendly hash function, and an entire specific purpose hasher chip for it, so that computes a lot of these hashes in parallel, so to speak. So also there, because the hash uses a lot of lookups, you need also a lot of columns which will be subject to one and the same table lookup. But beyond that, what is often not explicitly called a lookup anymore is the same techniques that LogUp uses can be used to prove the data bus between different components of your CKVM. That's exactly the track of Polygon Maiden. If people are interested in that, I can spend some words at the end of the talk on it. But in general, I will now go back and focus on lookup application. So what will the talk be about? First of all, I'll give some context. So we will start off with permutation arguments and lookups. Second, I will then describe the classical LogUp protocol and what's the base principle. And the base principle is very much the same than that of lookup from Gabison and Kovatovich. We use poles instead of zeros. That's the other paradigm, which is very useful in the context of lookup arguments. And then, so that's essentially what is covered by the ePrint from last year. And then I will dive into the new publication with Shaha Papini, which shows how to use GKR, the Goldwasser-Carlyle road clone protocol, actually a protocol from the, I would say, the pre-SNARK area, how to use that protocol to highly optimize LogUp, in particular the commitment pressure of LogUp. Okay, just for completeness, I mentioned already one of the works, not two of them. I mentioned lookup and CQ. So lookup, just as far as I remember, it just happened to be released like 1 week before I released my LogUp paper back then. Which was a bit unfortunate for me because they completely stole us the show. Anyway, so lookup does the same. Not actually, they address already large table lookups, but there is one protocol which I call the proof of radical, which is exactly the same like LogUp for a single column, for a single witness column. And before that, I was more formulating what lookup calls fractional decomposition. I was putting more in the context of the formal logarithmic derivative, but essentially it's exactly the same. So but logarithmic derivatives and its usefulness in the context of permutation arguments or lookups, or permutation arguments at least. I mean, I was not the only one that was thinking about it. There's Liam did Bulletproof plus, which was like a couple of months before lookup, which I wasn't aware of, and he also already uses the logarithmic derivative. To be frank, I never read the paper, so please don't ask me what the concrete application is in this case. Okay, and then CQ, which I mentioned already before, large table lookups, Liam, Egan, and Gavison. Okay, some background. So what's the classical approach to tackle permutation arguments, or let's more concretely, multi-set equality? So we consider we have given two sequences, the witness sequence, the WI, and another one, TJ, typically. Yeah. And we want to prove that one is the permutation of another. So both can have multiple occurrences of one and the same value. It doesn't matter. So we want to have multi-set equality. So it means each value that occurs here with a certain multiplicity occurs here exactly with the same multiplicity. And that's simply done by encoding the elements in the sequences as zeros of polynomials. It goes back to Bayer and Groth, I think it was 2012. So because they're the same up to permutation, if and only these two polynomials in the code, the zeros are the same. And how is that proven? The polynomial itself is kept virtually, but one samples a random value alpha for x and proves that identity at that random point instead, which leads to a grand product. And if you use grand product arguments from Planck, that's efficiently doable. For lookups, it's a bit slightly more complicated. it's not slightly more, it's let's say it's substantially more complicated. It's about set membership. So that is now, I've given a table sequence Tj. Typically, I don't have multiplicities there, or they're all only single occurrences to make it simple. And you want to show that each element of Wi is contained in the table. That means Wi might call a table element several times, whereas in the table it occurs only one time. In other words, I call this set membership. So if you collapse down the sequences to sets, you remove multiplicities, then the sequence of the witnesses, the set of the witness elements is contained in the set of the table elements. And that's the case if you now try to pull that over to encoding elements as roots of polynomials, you need to talk about, you need to take the multiplicity of how often a table value occurs in the sequence, in the witness sequence, by the exponent, yeah, I think, I'm sorry, not directly got the sentence grammatically finished, but I think the idea is clear by the formula. So you want so that means Wi is contained in the table as a set if I can find multiplicities such that this identity holds. And again, you just sample at the random point and prove that at the random point. But the problem is exactly that the multiplicity, something that is provided by the prover, typically, is in the exponent. The ARIA paper from 2018 addresses this identity by providing a bitwise encoding of the multiplicities. So that means and decomposing this product into into products of two-adic powers of that witness sequence. And that's doable. You have to prove these two-adic powers. You provide them. You prove them. Typically, if you want to keep the degree of your program, of your constraints low, but it costs at least as many commitments as you have bits in the multiplicities. So that's one way to do it. A better way to do it is lookup. So this representation I think I have from the Hyperplonk paper. It's not exactly the formulation you find in the lookup paper, but something equivalent. So if you want to prove that the witness sequence is contained in the table sequence as set, then you consider for that sequence the differential. I call it the differential. So it's something like at the point k, sorry, I'm jumped back. I accidentally clicked the mouse. So given a witness sequence, any sequence, let's call it AI, then you just look at the pairs of two adjacent values in time, AI plus 1. That's like a vector. I call it, it's the difference. You can consider it as a sort of difference vector. So, and what they say is, if you look at the sequence, if it's if it's contained in the table, then the only differences that it's a bit, I haven't thought of that long ago, but you provide this function S is a sort of integral. That's why I call it integrability criterion. So you provide, so you name all the differences occur from the table sequence itself. It's like the table itself provides a grid. It's like a basis grid, and the only thing you need to assure is that two adjacent WIs, if the difference is larger, that it's split into these smaller ones. It should be guaranteed, but this criterion, sorry, I did not prepare on the context here. It should work. I once understood it, but right now I can't improvise good enough in that way. But that's the way. So these are sets if and only if there exists such a sort of integral function, so that these two sets of the differentials are the same. So you bring all the differentials, the one that are, I think I'm returning to that, all differentials, the one that comes from a table and the one that takes into account multiplicities, which means like you don't have any difference. You bring that under the hood of a single function. That's the integral. So, or in polynomial identities, you encode these vectors by, just doing, considering linear factors as the roots of the polynomial. That generalizes easily. You just sample now for both y and x a random point and end up again with the grand product argument. Okay, so the big picture here is, so we start with the witness columns, we have the table column, and we need to provide that integral for the differentials. That integral, and that's as large as the union of the witnesses and the table. So this is really as large as the same thing. So that you need to provide in any case. Then you sample the randomnesses to reduce it to a grand product argument, and you need to provide the running product for that grand product argument. I want to normalize these pictures, though there are always trade-offs between the degree of the program and the number of commitments to be provided. But I normalize all my observation to the case where we only have degree 2 constraints, which means that the running product goes over the same domain as this sorted union is large. Okay, so that means you provide all over. It's like you need, that's needed anyway, and you need to provide twice as much. So overall, you have another 2 blocks of the same size, and that's very unsatisfactory. So this is the situation that you face with the multiplicative view of lookup. LogUp follows the same principle as lookup. So the main difference is now we did just use a different algebraic object, not polynomials. So we don't encode our elements as zeros of polynomials. We do otherwise, we encode them as poles. So that means for the witness sequence, you just add for each element pole, and for the table the same. And the nice thing about poles is that multiplicities, they're not in the exponent, they're not powers of linear factors corresponding to roots. Multiplicities are now just scalar how often the pole is taken. So poles just sum up in the fractional discourse that they easily. So, and that's the core lemma. It's just the uniqueness of fractional decomposition. So consider we have two sequences. And consider that the witness sequences actually should be the length plus. No, it's good enough to just for the witness sequences. That the length of the witness sequence is smaller than the characteristic of the field. That's important. I will tell you in a second why. So and then you can say, okay, the one witness sequence is in the other if each value of the table occurs with a certain multiplicity. The point is, so this must hold as rational function. The point is, it's important that this composition is unique, and that which has to do with that if you would add the same pole characteristic many times, you would end up with 0 again. So poles cancel out if you sum up the poles. But if you per se say my witness sequence is anyway smaller than the field is large, which in most application is the case, one has to be a little bit careful when one uses very small fields like M31. But in general, you never hit the characteristic boundary in any case, and you can say, okay, the sequence is contained in the other as sets if and only if I can provide multiplicities so that these two rational function fractions or fractional decompositions are the same. Yeah, and then you just sample alpha for x randomly and end up with a subcheck of fractions, fractional subcheck. So fractional subchecks are typically proven by making the 1/over term the inverse by providing a polynomial for that inverse and prove it to be the inverse. And that causes that for each of the witness sequences, and also the table sequence, so all of them, they are subject to the fractional subcheck. Each of these sequences, you need to provide one for the inverses, essentially. So these are the helper functions here. They're just needed to turn a fractional subcheck into a polynomial subcheck. And the polynomial subcheck is proven using standard techniques, like running sum argument. Sorry?
How costly it is to actually compute those helper functions? Like, are they trivial to be derived? Or do they involve
computing is not so much the problem. Committing is the problem.
Fair enough.
That costs. So they need to be provided and to be proven to be the inverses. That's the classical way one follows here. So
okay, fair enough.
And once you have them proven, you do the sum check actually over these helper functions instead, which are the inverses. That's the fractions, which are the fractions. So yeah. But as you see here, if you have in mind still the picture we had with lookup for the many columns case, where we had this block by the amount of data to be committed on top of it another 2 times, we are now somewhere where we only have it just another time instead of 2 times the same block. So it's like a 3-to-2 improvement.
I see. So that means that for multi-column lookups, this is definitely the way to go.
Exactly.
Yeah,
Exactly.
makes
There
complete
is
sense.
it's not the way. If you have just a few columns with a single column, I have to double check here. It's definitely not better, I think, or about equivalent. So, but the big benefit becomes feelable if you have many columns. In original LogUp paper that from 2022, I'm even trying to predict in terms of operation counts where the sweet spot might be between when one does on top of it the trade-off between higher degree program, not degree 2, higher degree constraints versus for paying with higher degree constraints for less commitments to be given in the helper functions by providing helper functions for groups of inverses, for groups of columns, for the inverses of groups of columns. That's doable. That's our standard techniques in this trade-off. I'm not going to talk about here. So essentially, that's the thing to make it comparable with lookup. Also, both use degree 2 programs, and we already have an improvement from 3 down to 2. Yeah, but actually, one can do better. And that's essentially the insight of Shahar Papini, inspired from our discussion we had when reading the work of Justin Thaler in the context of the lasso lookup argument. It's just a quite small note that where he refers to a previous work of his, that you can do the grant product argument using GKR. To be honest, I always looked at GKR. I didn't take GKR. I underestimated its usefulness. But that comment made me think about reconsidering GKR. And it turns out that you can use GKR also in this situation. And the nice thing of GKR is that you don't need to provide any additional commitments. I will go into that in the next slides. So let me go once back. So this was the initial LogUp 22, but we can get completely rid of all these helper functions, ending up with a single extra column to be provided. It's the multiplicity column, and that's beautiful in my opinion. So let me try to explain GKR. Not in all generality, but in that specific case that we face, which is a very simple circuit in the end. So dates back to the pre-SNARK area, essentially. And it's made for layered circuits with a few rows. I consider a layer of the circuit as a row. So you have few rows, and it's similar to an air. It's not exact. It's not the same, but I like to view it as a horizontal air, where instead of encoding columns at polynomials, you encode really each layer, each row. You have a single polynomial. It's a multivariate protocol. So in our case, it's a multilinear polynomial. One row, one layer. By layer, we have one multilinear polynomial. And the constraints between two adjacent rows is formulated via a sum check. And the protocol will be a multi-round protocol for each step you do from the top layer down to the bottom layer. Something like input layer or output layer to input layer. So that's how the circuit for our fractional sum check will look like. So that's a computation we want to prove. So we have given, I'm assuming here a bit knowledge about multivariate provers. For those who are not familiar with it, just ignore that for the basic idea. So this is the hypercube here. So I've given two multilinear polynomials. So put two functions over the n-dimensional hypercube, or the n-dimensional Boolean hypercube. And I want to prove that the sum of their fractions is equal to a claim P over Q. Two numbers that I provide. Circuit goes as follows. It's like every sum check or ground product, it's a tree-wise circuit. So on the bottom layer, it's the layer for the hypercube of dimension n, we have given all the p's and the q's, all the numerators and the denominators of fraction I want to sum up. In each, so from layer to layer, I just sum fractions pairwise, and that reduces the size of each layer, the horizontal size, by a factor of 1/2. And that is done recursively.
Ulrich, could it be possible to have a different arity and like go faster towards traversing towards the root? Or it wouldn't work?
That's doable, but it will increase the constraint, the degree of the constraint between two adjacent layers. And I think in the end, you don't win much, if anything at all, is my feeling here.
Okay.
So we will see how the constraints look like. In our case, there will be only degree 2 constraints if you do it really pairwise, halving at each step.
Okay.
But yes, you can do faster steps at the cost of the degree of each constraint you have between two adjacent layers.
The expression degrees is still a power of 2 always. So you jump from 2 to 4 and from 4 to 8 and so on.
If you want to keep with the pure two-adic setting of hypercube, then it's then the radix you would choose would be a power of 2.
Okay, and in that regard, have you done any kind of analysis on the possible the combinations of different arities and the, like for instance, I don't know, if you use an arity of 7 or I don't know, something like that, that it's like almost at the limit or something like this?
We didn't do something like this yet. In general, my feeling is often that's similar, like also to mixed radix FFT in the univariate sense, that the improvement when going to a non-two-adic setting is probably not worth the implementation effort. So that would be a measure you do only if you need to push out, if you need to squeeze out everything you can. So it's currently, I don't know if somebody did already implement it, but both Starkware and we at Polygon, we didn't implement it yet. So for that paper, we just did some hand-wavy operation counts again, which are a quite unreliable measure, but at least an indicator for the performance of the end of LogUp using GKR.
Okay, thank you very much.
Okay, so that's the circuit. It has a tree-wise topology. Each gate does the same. You take two, so you keep track of numerator and denominator in each step. So it just does the sum. Oops, what happened? What's happening here? Do you see still my screen?
No, we lost it now.
Okay. Is it back?
Yeah, it is. All good now.
Okay. So again,
Yeah, we lost it again.
I'm just using the arrow button. So let me reshare. I want to switch the slide. It doesn't let me. So if you look at one of these gates, it's just the addition gate of two fractions. So let's assume we have the point x. X is actually seen or consists of many coordinates, but I didn't use the vector notation here in this slide. So at a point from the at the point in the k-dimensional hypercube, numerator and denominator is formed from numerators and denominators from its children nodes, which according to the topology of the hypercube just means you take that vector x and append either a 0, that's the left child, or a 1, that's the right child. And the addition law is quite simple. For example, the numerator, I mean, you know how to add two symbolic fractions. The numerator is the product of the left child numerator times the right child denominator plus the left child denominator times the right child numerator. We'll see it in the next slide. Though in that slide, I will immediately describe the entire sum check you do on the polynomials. So look at this. This is just the Lagrange representation. That's what other papers call the EQ function. So this is just the Kronecker delta. So how to read this? Don't look at too many details, but at a point, so we are now at layer K, and we want to formulate its dependencies on the numerators and denominators polynomials values at the layer below. It's k plus 1. So we have pk plus 1, qk plus 1 that encode numerator and denominator. And what you see here at point little x over the k dimension, we have exactly the law I was mentioning in the last slide. So that means that reflects exactly the numerator when adding the symbolic fractions from the children nodes. And the same for the denominators, even simpler. It's just the product for the least common, not the least, but for a common denominator. But this just mimics symbolic addition of two fractions. And yeah, so what here is the entire system to be sum checked at each step. So how does the proof go? You start with the top layer claim, which is a constant polynomial because it's the zero-dimensional hypercube here. And then, you pointwise, so you reduce that representation from a linear sum using Lagrange representation, you reduce that to a sum check of scalars. I was skipping here a little detail. That top layer idea is a bit problematic in this writing because the zero-dimensional hypercube is an exceptional corner case. But think of it that we would have just two tops for a second. So we would start at layer 1 instead of layer 0 to make it simple. So we have a one-dimensional hypercube. That means you make a linear combination of these two sum checks. This is sort of batching. which means that you want to know that top layer polynomial at a random point. So that so in other words, and at that random point for capital X, if you insert a specific value, you have in fact a sum check of scalars and not of polynomials again. So in our settings, so you start with the claim, reduce it to a claim of the polynomials of one layer below at a random point. This random point is sampled in the course of the sum check protocol and so on. Then for the both of things, you do a sum check and reduce it to a claim of the polynomials another layer below, which is the layer over H2, and so on, until you end up having overall reduced the initial claim to the evaluation claim of polynomials at the bottom layer, which are the polynomials subject to the fractional sum check. So this is how it goes. You don't need any commitment in between. None of the intermediate layers are committed. You repeatedly use sum check 1 for each layer transition. First glance, it seems like it would be quadratic effort, but it's not, because they shrink, or let's say they increase if you go from top to down, or so they increase geometrically, or they shrink geometrically if you go from the bottom layer up to top layer. So that stays linear time in the number of field operations. Okay, quick recap here, just the picture we have in mind. So besides what is needed to be committed anyway, that's the witness sequences subject to the lookup and the table, we just have to provide a single extra column for the multiplicities. Then the verifier sends a random point. And on this random point, this defines at which point we do the fractional sum check. And we run the GKR circuit repeatedly sum check in order to reduce to a multilinear evaluation claim of the involved polynomials, which are numerator polynomials. Most of them are trivial, like they don't have any numerator, it's the constant 1. The numerator of the m over t minus alpha, you know, that's the numerator for the table part is m, the denominator is t. So that domain, that circuit, the bottom domain is as large, is a hypercube that is large enough to host the witness sequences and the table sequences.
One question: when you said now that kind of the default element is a 1 instead of a 0, could you explain why?
If you remember how the sum check was looking, I can jump back a few slides.
Or whatever you prefer. If you want to finish,
I try first with words. If this
sure.
doesn't. So what is the sum check to be proven in context of the lookup? It's like the sum over 1 over the omega i's, wi is the witnesses, minus alpha, that pole evaluated at alpha, the omega I pole at alpha, that sum must be equal, it's 1 over, because it's 1 over, the numerator is equal to, and then we have this, or let's say, is equal to the sum of m over t minus alpha.
Okay, I see. Because if it was 0, that you could, as in Lasso, you could take profit of that and use a sparse polynomial commitment, so that you even pay less, because all of the things that are 0, you can directly omit them.
So sorry, can you repeat?
So yeah, I asked that because if the kind of null elements, or elements that don't bring, like, I don't know how to say it, that are like the defaults basically, if they were zero, you could be able to use a sparse polynomial commitment, and therefore take profit of all of the zeros by just not needing to commit to any of them directly in first place.
In
But
this case, the
yeah,
witness data itself and
it's never sparse, it's always dense, right? Like you have,
stands.
yeah, I see.
What is sparse is, in a sense of representation, the multiplicities are small values. I wouldn't call it sparse. So it's not in the sense of sparse polynomial commitment scheme.
Yeah, I see.
So we, this column consists of typically small values. Depends on how large the multiplicities are. At maximum, as many elements you have for the lookup.
Fair enough.
So, for some commitment scheme, that committing M is quite cheap for the situations we face at Polygon, which are Starks. That doesn't matter having small values or not, because with Solomon codes blow up to when you consider just the LDE evaluated out the interpolant using from small values to some other cause set, you have arbitrary values that look like random.
Okay, fair enough. Thank you for your answer.
Okay, so yeah, that's the big picture. Just a single extra column to be committed on the cost of the GKR, which is arithmetic cost, more on that here. So, so we get rid of all these helper functions to be committed, but by a more complex arithmetic protocol. And if you run a univariate proof, because GKR is multivariate, you need something, what we call the Lagrange transform in the paper. Something that, which is a transform, and yet another transform from, which turns a univariate polynomial commitment scheme into a multilinear one, so that you can prove multilinear evaluation via a univariate IRP. So I won't go into details here, but it's a quite cheap and elegant protocol. Costs just an extra commitment, which is essentially the multivariate Lagrange at the query point that is obtained in the course of the GKR. Actually, the last sum check of the GKR. So, but in a multilinear case, multivariate case, it's just a single extra column. And when thinking about the expected speedup, that is with a massive grain of salt here. For easy commitments, it's quite easy to estimate. I have even was relying on benchmarks that I did in the LogUp 22 paper in order that compares the cost of ordinary field multiplications, or measures the commitment cost in field operations, in the equivalent number of field operations by timing, equivalent number. And for EC-based commitments, I'd expect an absolute lower bound of improvement here. If you have a large number of columns, that's always the important thing. So for the situation we face, would be more than tenfold. When going to Starks, it's a bit more difficult to answer, because the commitment cost very much depends on what type of hash you use. But committing means not just hashing. It means you, for Reed-Solomon, you first need to compute the interpolant and evaluate it over the entire sampling domain. So you need to compute extrapolations. And they're already costly in some sense. So they have some arithmetic cost. And the arithmetic, just by operation counts, not the best measure for real-world performance, but just by operation count, the encoding effort of Reed-Solomon is quite comparable already to the GKR effort. And that leads us to the estimate or expectation that speed up here is barely influenced by the type of hash you use. And even if you use a very fast hash, like Blake 2 or Blake 3, or monolith, yeah. If you use very fast hashes, then we expect it will be rather approaching only to be a twofold improvement. If you use slow hashes in primitive, like Poseidon, or even more like Rescue Prime, then it approaches the tenfold improvement because committing becomes more expensive. So that's what we expect, but with a massive grain of salt here. So we are curious how it will be in real-world implementations. So I'm not sure how much time did we take.
We took exactly 1 hour. But like, I don't know if you have any time limitations, but from our side, we will finish, if it's okay from your side, when people has asked all of the questions that they might have.
Yeah, I'm open for questions.
Okay. So yeah, now it's time everyone to just jump in and ask, or put it in the chat and I can read them loud, whatever you prefer. On the meantime, if no one has
yeah,
any,
please read. Yeah, other questions?
I have one, if no one else has. My question is regarding the rounds that you have in GKR. So how are you representing as an as kind of an arithmetic circuit or Boolean circuit? I don't know how to say, the sum of fractions, because a sum of like, at least for the school, like the naive fraction, in the real domain, like in the real numbers domain, to sum a fraction, you need to do much more stuff that like simply decomposing it into bits and just adding and subtracting some things. Like you need to have common denominators and this kind of stuff. So
I'm not sure if I understand the question, but the circuit we use here is not a Boolean circuit.
Because you can perform addition instead of and
over the field we are using. The thing is, we are doing symbolic fraction arithmetic. So it's like a fraction is not really, if you divide numerator by denominator and it's a single field element, it's really, we keep track of numerator and denominator as a vector.
Oh, I see.
So it's like a symbolic fraction.
I see.
And we compute the symbolic fraction of the fractional sum check. So we do symbolic operations here, but these are all over the base over the field that we are using.
I see. That makes sense. That makes sense now. Okay, that answers my question. Yeah, thank you.
This makes it to this, yeah. So it's in the end, if I jump back here, is my slide still presented?
Yeah, we can still see them, yeah.
Okay, try to go back. Yes, that's the way you do it. So it's really you start with field values, vectors at each, if I just take one gate, at each input, the two inputs, they're like symbolic fraction. Numerator, P, Q, P for always for numerator, and the PQ of the of this input and PQ of the other input. And the symbolic representation is just pure polynomial expression, you know? You take just the product. This is just the product of the pk plus 1 left times qk plus 1, the denominator of the right, plus, you know, it's just the ordinary law, you know, for integer.
I see.
fractions. You know?
Okay. Now that makes sense. I got lost here. Yeah, my bad. That makes complete sense now. Thank you very much. I do have another question, but if anyone has other questions, like feel free to say it or interrupt me or whatever. So when you got to this improvement, and now that you have like this is pretty recent, of course, but do you think there's any kind of, or you foresee any kind of way to continue improving via GKR or via any other way, LogUp? Does something ring a bell for you towards maybe we should look into that direction or something like this?
Not. We didn't think about it yet. Or at least I didn't.
Okay.
So I also never thought about what would be time optimal here. My feeling is in terms of commitment effort without multiplicity. Just a single column is quite good. Don't know. Don't know if there are further improvements here. I mean, there are possibilities, as you pointed out in a previous question of yours, to do a higher radix step, but I think one has just to write down the cost of the sum check of having increased degree, but roughly it's, I would say you lose what you win few steps, but each step is more costly here.
That's fair.
Because of the higher degree. So yeah, short answer. I don't know.
It's also true that, like, of course, not for the bottom rounds, but I don't know at which point in the heath of the tree, but you can definitely pre-compute, like, have pre-computed tables for a bunch of the operations that you will perform on the tree, at least up to a particular heath. Like, of course, for 250 something bits, it's definitely not feasible. For 32, even not probably. But maybe at 16 bits, you can already have a pre-computed table that speeds up like this part of the tree towards the end.
I mean, this tree here is takes witness data from the bottom, so I wouldn't know how to use pre-computations here.
But even if you use pre-computed data, even if you use only witness data at the bottom, it doesn't mean you don't need to compute the operations in the intermediate levels of the tree, right?
I mean, typically that's what you do as the prover. You do step. First, start with all the values at the bottom layer hypercube. Make the pairwise sums. You have the values over.
Oh, I see.
Half the size.
Yeah.
And so on and so on. That's how you. So I wouldn't know how to improve here. But a question is that I entirely ignored from my point of view is how dealing with larger tables. How about having several table lookup? We call it cross table lookups. Fractional sum check they don't batch well. Polynomial sum check batch well without increasing the degree. Neither domain size nor degree of constraints. But fractional sum check don't batch that well. So
you cannot interpolate them or do anything.
I mean, if you just say I want to batch them over the same domain, it just means you increase the degree here.
Okay, fair enough.
The P of Q over Qs of different, which are subject to different sum checks. If you write the symbolic representation of the sum, you have them of corresponding higher degree.
Makes sense.
So
yeah, it's an interesting topic anyways, definitely. Thank you very much for your answer also, Ulrich.
You're welcome.
Okay, if no one has written anything, I don't see anyone asking anything else, so I will assume there's no more questions. From my side, I want to say thank you, Ulrich, because this was a really nice presentation. At least from my side, it's one of the presenters that I've understood the most things, to be honest. So yeah, thank you very much. It was really, really, really nice. It was really good and really insightful. So I guess that's it. Thank you very much for coming here and talking about LogUp improved to us. As said, it was really insightful and hope to see you soon here again for the Reed Solomon over the Circle group. Thank you very much, Ulrich.
Ciao.
Cheers, everyone.